For over 100 years, physicists have waited patiently. Since 1916, when Einstein first published his theory of general relativity, we've known, at least in theory, that something strange could exist in the far reaches of space. Something dark, invisible, and infinitely powerful. A cosmic monster so terrifying that not even light could escape its grasp. Today, we call it the black hole. But only now, with modern technology and relentless scientific effort, have we begun to truly peer into this abyss. And what we've found might just change everything. Black holes aren't just massive, they're mysteries wrapped in gravity. Imagine an object millions of times the mass of our sun, yet completely invisible. A place where space and time collapse, and the rules of physics begin to melt. For decades, black holes were just mathematical ghosts. But through relentless research, observation, and theories tested at the edge of human understanding, we've moved from ignorance to awe. The journey began with Einstein's equations. But it wasn't until the 1960s that scientists found actual evidence. While studying the Cygnus constellation, they observed a bright blue star emitting X-rays, orbiting something. Not a star, not a planet, but a gravitational well so deep, light itself couldn't escape. That invisible giant was later named Cygnus X1, the first black hole ever confirmed. And with that, the hunt was on. Today, we estimate there may be over 100 million black holes in the Milky Way alone. But because they don't emit light, they're incredibly hard to detect. Still, their presence is undeniable. The closest black hole to Earth is just 1,500 light-years away. Far enough to be safe, but close enough to make us wonder. In 2021, science took a historic leap forward. Astronomers captured the first clear image of a black hole, the M87 black hole, 55 million light-years away. But the photo wasn't just one image. It was a composite, stitched from observations across several nights. And what it revealed was shocking. A black hole isn't just a gaping void. It has structure, layers. First, there's the event horizon, the point of no return. Once crossed, nothing escapes, not even light. Next comes the photon sphere, where light is trapped in endless orbit. And finally, at the center, the singularity. A point where all matter is crushed to infinite density, and the very fabric of spacetime tears. It gets stranger. Each black hole is unique. Some spin, some feed on stars. Others drift silently in the cosmic dark. But one thing remains constant, their power. If you fell into a black hole, you'd be stretched atom by atom in a horrifying process called spaghettification. Your atoms would never return. And even the most advanced spacecraft wouldn't stand a chance. Because we can't send probes into black holes. Everything that crosses the event horizon is lost forever. Scientists have to study them indirectly. By analyzing X-rays, radiation, and the motion of nearby stars, we piece together the mysteries. But it's not just about what's outside a black hole. It's about what might be inside or even beyond. In 1963, New Zealand mathematician Roy Kerr revolutionized our understanding. Using Einstein's equations, he described a spinning black hole, not one that collapses into a point, but into a ring. This ring, spinning so fast that centrifugal force keeps it stable, forms something incredible, the ergosphere. But Kerr's model hinted at something far more exotic, a wormhole, a theoretical tunnel through spacetime. What if, instead of being crushed, something falling into a black hole could travel through it, exiting into another region of the universe or another universe entirely? This idea leads us to the Einstein-Rosen bridge, a wormhole that could connect two separate locations in spacetime. It's the stuff of science fiction, but grounded in mathematical reality. Imagine folding a sheet of paper in half to bring 2 points together. That's what a wormhole could do, connect distant points instantly. However, there's a problem. Wormholes, as we know them, are unstable. They collapse almost instantly. And even if we could stabilize one, Einstein's theory of special relativity says nothing can travel faster than light. So interstellar or time travel through wormholes remains, at least for now, impossible. But some physicists aren't giving up. One of the most famous among them is Dr. Michio Kaku. For decades, he's worked on what many consider the holy grail of physics, the theory of everything. a single framework that unites Einstein's gravity with the quantum world of particles and energy. And the best candidate for that theory is something called superstring theory. According to superstring theory, everything in the universe is made of tiny, vibrating strings. Different vibrations create different particles, just as musical notes come from different vibrations of a violin string. But here's the twist. For the theory to work, it requires not 4 dimensions, but 10. These extra dimensions are curled up, hidden from our view. Imagine an ant walking on a tightly rolled piece of paper. To the ant, the world seems flat, but from above, we see the curves. Similarly, we live in 4 observable dimensions, but the universe could contain many more, wrapped tightly, influencing our world in ways we can't directly see. String theory suggests that black holes, wormholes, and even the entire universe could be explained as vibrations in this multidimensional fabric. In fact, black holes might not just be cosmic vacuum cleaners, they could be gateways. And incredibly, we may already live inside one. Dr. Kaku suggests that the Big Bang might not have been a singular explosion. Instead, it could have been the birth of a universe from a wormhole, an umbilical cord connecting one universe to another. In this view, our universe could be the interior of a massive black hole that formed in another universe. And the black holes we study here, they might lead to entirely new realities. Think about that. The cosmos isn't just stars and galaxies. It's possibly a network of interconnected universes, each with its own rules, physics, and timelines. Traveling through a black hole could mean being reborn in another universe altogether. But there's still work to do. Solving the mystery of black holes requires us to go beyond the known, to unify all physical laws. Superstring theory has shown promise, and in recent years, scientists have made breakthroughs in understanding quantum black holes. While full 10-dimensional solutions remain elusive, progress in lower dimensions suggests that we're inching closer to the truth. Edward Witten, one of the pioneers of string theory, once called it 21st century physics that fell into the 20th century. Now, as we stand midway through the 21st, that statement feels more prophetic than ever. Black holes are no longer just terrifying anomalies in the sky. They're cosmic laboratories, portals, engines of creation, and possibly the key to understanding everything. So as we peer into the dark heart of the universe, we're not just looking at a void. We're staring into a mirror reflecting our deepest questions. Where do we come from? What is space? What is time? And could there be more? Because the more we learn, the more we realize we've only just begun.